Hidden in rugged and remote fiordland in the southwest corner of New Zealand's South Island is the Manapouri hydroelectric power station. Constructed in the 1960s, the scheme draws water from Lake Manapouri to an underground powerhouse and then through a 10-kilometre Tailrace tunnel to Deep Cove in Doubtful Sound. About 180 metres below the level of Lake Manapouri, the station has never performed as well as it should, and to remedy this, a second Tailrace tunnel is being drilled. The upgrade will add around 640 gigawatt hours per annum to Manapouri's output, enough to meet the needs of 64,000 households. Work on the new tunnel started at Deep Cove in early 1997, following 4 years of investigation by the state-owned electricity corporation ECNZ. In 1999, the government split ECNZ and the newly created Meridian Energy took over the Manapouri project. The contract was awarded to a joint venture of Fletcher Construction of New Zealand, Dillingham Construction of the United States and Ilbau of Austria. While the first tunnel was a traditional drill and blast job, the second will use more modern methods, namely a specially constructed tunnel boring machine, or TBM. Among the preparation needed before the TBM arrives on site is excavation of about 50,000 cubic metres of earth and rock in front of what will be the new tunnel portal at Deep Cove.
The problem with the existing arrangement is that the water from the lake, it falls 180 odd metres vertically to the power station, which is at the underground at the head of the lake. From there it has to flow away through a 10-kilometre long Tailrace tunnel to emerge at the head of Deep Cove. The actual friction or hydraulic resistance in that tunnel is higher than what it was thought it was going to be, and as a consequence there's more back pressure on the turbines. The second tunnel, in fact, lets that water flow away more easily, reduces the back pressure, and enables the station's output to be increased for much the same volume of water. And someone once likened it to sort of putting a free flow exhaust system on a car. It's that type of concept. We're not actually intending to raise the lake, use any more water, it's just simply making a more efficient use of an existing resource.
While the tunnel will be drilled from Deep Cove, major work is also required at the other end, called the headworks at the west arm of Lake Manapouri. A temporary ventilation duct runs down the existing power station access tunnel to the site of a new underground excavation. A new access adit will link to a maintenance shaft and stop log shaft, which along with the first 150 metres of the new tunnel will be excavated before the TBM gets through from Deep Cove. Completion of this work will later require the power station to be briefly shut down. The new access adit is driven using drill and blast techniques. Back in the 1960s, when the Manapouri power station was constructed, these were the only methods available.
500,000 tons of rock will have been hewn out by the time the vertical penstocks, the spiral access road and the huge machine hall are finished. The hall alone will be 362 feet long and 130 feet high and house 7 huge turbo generators producing 700,000 kilowatts of electricity from the waters of Lake Manapouri.
Today's project builds on the engineering achievements of the original workforce.
You've got to have a lot of admiration for the people that came here into a wild area where there was just no access, no roads. They basically had to carve themselves a niche in the rock. We've been fortunate to be able to build on that infrastructure that's already been there. We've had a wharf there that we can unload the TBM on. We've had a road linking Deep Cove and West Arm. The barges have all been there. I think the tunnelling technology, of course, has changed dramatically from that time.
Changed too is the workers' accommodation. In the 60s, the fashion was rows of identical huts.
It's a single men's camp. The scores of huts were all brought in across the lake by barge and stand now in regimental rows. Today's accommodation block is on the same site, but fashions have changed.
It's painted green to help it blend in with the surrounding Fiordland National Park. The kitchen operates pretty much round the clock to fit in with shift work. Built to hold 150 workers, the hostel will later be extended to accommodate 180. The buildings were prefabricated and brought across Lake Manapouri by barge. When the project's finished, they'll be removed and the site will be reshaped and replanted. At Deep Cove, a temporary bridge is constructed over the existing Tailrace channel to provide access to the area where spoil from the new tunnel will be deposited. With vegetation cleared and initial excavation complete, the shape of the new tunnel becomes clearer. On September the 23rd, 1997, tunnelling proper starts with the first blast. A mobile processing plant is brought on site to begin producing the tons of aggregate needed for roading and concrete. Next to the main tunnel portal, an access adit is driven, which will also later link to the tunnel dewatering system. The walls are shotcreted. Drilling rigs are used to break up underground boulders so that later sheet piles can be driven to keep water out of the construction site. At the West Arm end of the tunnel project, work also continues and the access adit is complete. Excavation of the shaft for the stop log, which will effectively be the on-off control for the new tunnel, is well advanced. And similar progress is being made digging the new maintenance shaft. A couple of months after the first blast, the tunnel portal is taking shape and final shotcreting is underway. Though there's more material to remove before the TBM arrives, the access adit has now been pushed through and the drill and blast section of the tunnel has almost reached as far as it's going. To allow construction to proceed, as much water as possible has to be kept out of the site. To do this, interlocking sheet piles are driven round the perimeter to form a barrier. Previously, boulders beneath the surface, which could have made driving sheet piles impossible, have been shattered by underground charges. In front of the tunnel portal, wells are sunk to remove underground water from the construction site. 2 months before the TBM is due to arrive, the first concrete is in place on the floor of the tunnel portal and the drill and blast section is complete. It's been 10 months since work started at Deep Cove and the project is on schedule to have everything ready for the tunnel boring machine to start work. At the headworks, roughly 10 kilometres through the mountains at West Arm, excavation is nearly complete. One of the features of this project which makes it unique is the fact it's happening in a World Heritage Area, the Fiordland National Park. To safeguard this environment, stringent constraints are in force. With the TBM's arrival imminent, the ground on which it will be assembled is prepared to take its 1,000-ton weight. In the tunnel portal, reinforcing is in place for more concreting. All is just about ready for boring of the new 10-kilometre Tailrace tunnel to begin. A few days before the tunnel boring machine arrives, the portal is virtually complete and the precast concrete sides are in place. The TBM arrives at Deep Cove aboard a ship which has brought it from England. It will take days to unload and weeks to assemble. The Deep Cove wharf has been strengthened to take the TBM's weight. From the Deep Cove wharf, the TBM has taken piece by piece the few kilometres to the contraction site. It will be assembled on the specially strengthened pad in front of the tunnel portal. This will be kit set assembly on a grand scale. Meanwhile, in the tunnel portal, preparation continues to get the TBM into the tunnel. It needs a gentle slope, a decline of 12.5%, so the entrance is filled and will remain that way until the tunnel is completed. The TBM was first assembled in England, where it was tested, then it was dismantled for shipping across the world to Fiordland, where it's been put back together again. Although the giant machine was built by English company Markins, it was designed by US firm Atlas Copco Robbins. Ahead of the TBM, a gentle slope has been prepared. It'll take about 6 weeks to assemble the TBM and get it to the workface. Meanwhile, at West Arm, work continues on the headworks, and at the bottom of the stop log shaft, the stop log structure is taking shape. The TBM is 25 metres long and weighs more than 900 tonnes. With its trailing gear, the machine has a total length of nearly 500 metres and a total weight of 1,500 tonnes. Just over a month after it arrived, assembly is almost complete and the engineers give the TBM a spin. This is one of many milestones which will be marked on the Manapouri second Tailrace tunnel project. The purpose-built 10-metre hard rock tunnel boring machine is about as big and powerful as these things get. 1960s, the first one being used to drill a tunnel through soft rock in the United States. It's only recently that TBM technology has advanced enough to drive what at 10 metres diameter is a very large tunnel through very hard Fiordland rock. The TBM starts boring on June the 12th, 1998. On the other side of the mountains at West Arm, work continues constructing the headworks. Even with the latest in tunnelling technology on site, this is a challenging engineering job. Meridian's man in charge is Tom Martin, an American with 30 years of tunnelling behind him. He says one of the challenges on this job is Fiordland's geology.
It's still changing. I mean, we have reason to believe it's gone up about 50 millimeters since the last time they did the tunnel. So you've still got an active zone there where it's being raised up by the thrust from the plates, one underwriting the other one. And so you're in an active zone, and of course that means that anything can be in there. We presume it'll be very much like the first tunnel. But again, in most part of it, we're lower, and we're about 75 to 90 meters to the south of it, so it could be anybody's ballgame. The tunnel boring machine really, in essence, is just a great big drill. It grips the side of the wall of the tunnel, and that's what we call the anchoring point of the TBM, with about 3.5 million pounds. And then it exerts a force through some hydraulic cylinders, which are called thrust cylinders, and it puts about 23 to 24, 25 tons per cutter on the rock, and the cutters are arranged, even though they don't look like it, in concentric circles. As the cutter head revolves, these cutters bite into the rock, crush the rock underneath the cutter, or the ring of the cutter. The rock in between the rings, it gets spalled off. The bucket or opening on the perimeter of the TBM pick this rock up, they take it up to the top, where it falls into a hopper, and then it goes by conveyor belt all the way out to the muck pile or the silt pile.
The TBM eats its way through the mountains 1.8 metres per stroke. Buck Buchanan and the other drivers work shifts to keep the machine working round the clock. It's kept on course by computer, guided by laser, but the driver takes over each time the TBM regrips. The tunnel's designed to last at least 100 years, and to make sure of that, even the soundest rock is rock vaulted to increase its load carrying capacity. In the best, or T1 ground like this, where the rock stays intact, 8 rock bolts are installed around the top or crown of the tunnel. A crew of 25 man the TBM. The workers are protected from rock falls by the fingers extending back from the front of the machine. Their workplace is extraordinarily noisy. While the hardness of the rock did pose a challenge, a potentially greater one lay in another feature of Fiordland's geology.
We had about 6 major faults to go through. These are where the earth is relieved during events like earthquakes. So as the 2 blocks of rock slide beside each other, we get crushing and shearing of the rock. So the rock actually becomes like a soil rather than what it used to be. So through these major fault zones, we're mining into what could be described as a mixture of rock and soil.
So basically a really difficult place to put a tunnel when you've got faults around.
Yes, exactly.
As the TBM drills through those faults, sections known as T3, where the rock is least stable, special precautions are taken. Mesh called lagging is put in to hold any loose material in place and keep the circumference of the tunnel intact. Any remaining loose rocks are broken up. the while, drilling continues. When the going's good, the TBM regrips about once an hour. For extra strength, what are known as steel sets are placed in these sections too. The sets form rings round the tunnel's circumference. Designed to support 5 metres of rock load each, the sets are spaced at 1.2 metre intervals. Thanks to knowledge gained from the first tunnel, about 70 metres away, the project designers had a pretty good idea of what rock conditions to expect. With 5 faults to go through, they not only knew the sets would be needed, they knew where. The TBM leaves a perfectly round hole with unstable sections ringed in steel. Later they'll be encased in concrete as well. In T2 sections where the ground's not too good or too bad, the tunnel gets extra rock bolts and mesh. Then concrete is sprayed on, a process called shotcreting. The new Manapouri Tailrace tunnel is among the biggest through the hardest rock ever driven by a TBM.
This is a world-class project, and they don't come around that often, and so we're all really fortunate to be involved with this, and you know, it may be a long time before we get to work on something as big and exciting as this, and this is the type of projects that this is why I became an engineer, is to work on stuff like this.
As part of normal maintenance, the cutter wheels which grind their way through the rock are regularly changed. At every change, the outer ring is replaced and the bearings get less frequent replacement. At first, each wheel lasts 1 metre. But as the project progresses, the contractor FDI finds they can do 2 metres. As the TBM advances, railway lines are laid for the locomotives which ferry men and materials back and forth. For most of the project, 12-hour shifts are worked. Tom Martin says this is a unique project.
It's an active zone. It's got some real hard rock. It's got some sedimentary rock which has been metamorphized into some schist. The geologist on the site tells me we're seeing rock come out of the tunnel that hasn't seen daylight for probably 13 million years or better.
And the geology isn't the only challenge to be overcome on this job.
Environmentally, it probably has some of the toughest things I've ever seen. Number one, you have a TBM tunnel, which is 10 meters. That's big. Number two, you have a environmental impact because of the park. Number three, you have the park itself, which means that you have to clean everything and comply with all sorts of regulations. And then there's a camp job, and I've never really done a camp job. And to top it all off, the rock's fairly hard. 4 or 5 known faults that will issue a lot of water, and that's what really gives tunnelers problems, the water.
The water seeps down from the surface up to 1.2 kilometres above the tunnel, and peak water flows reach 1,000 litres a second. Being electrically powered, the TBM doesn't like water, which is as cold as 6 degrees, making working conditions miserable. And to make matters worse, water on the other side of the faults ahead of the TBM is under pressure. It's trapped behind clay, under as much as 400 metres pressure from above.
You can imagine if you punch through one of these faults and you go into this very high groundwater pressure, you can cause all sorts of problems. The high groundwater pressure can make the fault material run in on top of you and effectively bog up the TBM. So it's very important to de-water the tunnel in front of you, particularly through these major fault zones.
To relieve that pressure, drain holes are drilled ahead of the TBM. Most extend about 50 metres out in front, and even after the TBM's gone through, water pours from the drains. The contractor, Fletcher, Dilling and Ilbauer, has to meet strict environmental standards, and dirty water has to be treated before it goes into doubtful sound. Beth Massa is environmental manager.
This is our main water treatment facility. It's a lamella clarifier thickener. We take the water from the tunnel, it's conveyed across the conveyor bridge and through this pipe past an inline flow meter which measures the flow. The flow meter controls the dose rate of the polymer, which is the chemical we use to coagulate the particles and get them to settle out. So the solids drop down into the bottom of the cone, and the clean water overflows out the back of in the discharge pipe.
So what you're really trying to do is to get as much of the solid material out of the water so it doesn't affect the sound, basically.
That's right. The main contaminant in the water is, of course, ground up rock fines. The water that comes in through the walls of the tunnel is clean until it hits our active work zone where the TPM's grinding the rock up to fine particles. And while that's naturally occurring in this environment, the field environment doesn't receive a large amount of suspended solids in the water all the time. So we are basically chemically treating the water to get it to coagulate, settle out and to produce clean water, clean discharge.
To quickly cover scars left by the project, a nursery's been established and spoil piles are planted out with species grown from seeds collected in the area. Returning the site to a near as possible natural state is another of the environmental requirements to be met.
Two relics from the original project are still in service. One of the boats ferrying Meridian Energy staff, the other FDI personnel.
It takes an hour to get across Lake Manapouri to West Arm. At West Arm, the power station has been briefly shut down to allow divers and engineers to enter the existing tunnel. They're taking measurements so that a bulkhead can be constructed to fit tightly into it to shut out water running back with the tide from Deep Cove. This will allow excavation to connect tunnel number 2 to number 1. Over coming months, there'll be several more short shutdowns as preparations are made for that major job. Two years later, the temporary bulkhead is ready. Divers begin practicing fitting it in a template of the tunnel floating in Lake Manapouri at West Arm. Planning for this operation has taken months and it's on a strict timetable. So before the station is shut down, the divers have to perfect their technique for installing the bulkhead. The whole financial viability of the tunnel project depends on minimising the time the power station has to be shut down. Meridian Energy can't afford to lose its power for any more than 21 days.
The only thing that made the second Tailrace tunnel feasible was how long we shut the power station down. The numbers had been batted around at one point that it could be done in 18 days. It was decided to give a 3-day window to that in case of contingency, if you will, and allow it to be up to 21 days. But anything beyond that, there was some serious concern about the stability of the grid, about getting the power to TY, and these things really made a lot of people nervous.
Thank you.
So when the station is shut down, a highly detailed plan is put into action. Everybody knows exactly what their job is and is very aware of the timetable. FDI's man in charge is Dave Bock.
That type of thing, when you're trying to work to very, very strict, severe time deadlines, the planning is probably the most important part of it.
With the station shut down and water no longer flowing through, the divers will enter tunnel number 1 and install the bulkhead slightly downstream of where the two tunnels will meet. Then the water upstream will be pumped out, allowing the rock plug between the tunnels to be excavated. As soon as they can, men and machines enter the surge chamber beneath the powerhouse. The dive team has brought equipment on trailers which convert into floating platforms. After all the months of planning and practicing, this is it. The bulkhead is in 4 sections which will be floated into position. First into the water is the top section of the bulkhead. Once launched, the sections are pushed out of the surge chamber and into the top end of tunnel number 1 by the divers. The divers work in 2 shifts. While the divers work on, equipment's being marshalled for the next stage. "18 hours after the divers went in, the temporary bulkhead is in position. And 5 hours after that, the water has been pumped out on this side of the door, and not much is getting through from the other side. This has been a dream start to the outage.
Once it started, it just seemed to get better. We found a system which would block off tunnel number 1, was installed in about 18 hours, and the tunnel was pumped down in about another 4 or 5 hours. So in less than 24 hours, we had tunnel 1 down and walking around on it.
With tunnel 1 now closed and the water out of the way, work can now start removing the plug of rock between the 2 tunnels. Excavating the 10 to 20 metres of rock will be done from both sides. During earlier shutdowns, the access road has been improved, making it easier to bring heavy machinery on site. There are still 600 litres of water a second going through the power station for cooling, and it's taken away through this pipe. This is a drill and blast job. And before anyone really expected it, the breakthrough is made. At the same time as the excavation goes on, FDI are using a specially adapted hydraulic crane for rock bolting the existing tunnel roof. It requires extra rock bolts because there will soon be an increased span of rock to support. Over at Deep Cove, the Tailrace channel is still, and nothing's coming out of tunnel number 1. From tunnel 2, where the TBM continues working, spoil still comes out on the conveyor. The job runs day and night, and after a couple of days is ahead of schedule. The meticulous planning is paying off. Good planning means thinking of everything, even toilets. The pace has quickened at Deep Cove, where there's more spoil than ever to deal with, thanks to the TBM picking up speed. But the real interest is at the other end of the new Tailrace tunnel, which is now well on the way to being connected to Tunnel 1. But there's still more rock to be blasted. Safely round the corner, the crew await the blast. And once the all clear's given, it's back to work.
Can you find me another bit of hose?
3 days after the job started, most of the plug has been removed, and it seems probable the station will be able to resume operating well within deadline. The station shutdown's been timed to coincide with low summer electricity demand. Nevertheless, the sooner it's back in service, the happier Meridian Energy will be. Ten days after Tunnel 1 was closed off, the plug has been removed and rock bolting and shotcreting are finished. Soon the stop log can be lowered into place. All that really remains are the finishing touches, including cleaning out the drainage or relief holes which will prevent water from lifting the concrete floor. day later, the stop log which will seal off Tunnel 2 until it's finished is in place. It was manufactured by Sims Engineering of Dunedin. The junction of the two tunnels is now complete, with the remaining task being the removal of the temporary bulkhead to allow the power station to resume generation. But first, men and machines have to get out of the way. The pipe that had carried the station's cooling water away is removed, and now that water will refill the tunnel. Now it's the diver's turn again, this time taking the bulkhead back out. It's pretty much a reversal of what they did 10 days ago. The four sections of bulkhead are floated out of the tunnel and back to shore in the surge chamber. Once they've been taken back to the surface, they'll go across Lake Manapouri by barge and be transported to Twizel, where they'll be stored until they're needed again. They've been so successful, the design company Meritech has won the Gold Award of Excellence from the Association of Consulting Engineers of New Zealand. The stakes on this job have been high, the engineering challenge huge, and the conditions often trying. But at the end, Meridian's Tom Martin is a happy man.
By the time they finished, in something over 10 days, everything had worked excellent. The bulkhead had worked, the divers had worked, the drill and blast things had worked. The tunnel wasn't quite as far again as through there as we thought. It was about a couple meters shorter. The rock was better. There wasn't any water in there. And it just was a triumph, I think, of people and the contractor and the owner working together.
The next major tunnel milestone comes 3 months later. This is where the tunnel boring machine is expected to hole through, and its arrival is imminent. This is perhaps the most eagerly awaited event of the project. It's to be witnessed by about 100 people, including the men who have done the job, bigwigs from Wellington, and the news media. The tunnel boring machine's journey is almost over. It's been a difficult job and has taken about a year longer than expected, but with the hole through, that's forgotten, and there's a feeling of achievement. For tunnellers, this is what the job's all about. Though he's a veteran of many tunnels, Tom Martin can barely contain his excitement.
You can see the cutter head turning, the yellow cutter. I mean, it's spot on the ground, looks like.
It's taken the TBM just under 3 years to mine through the 9.8 kilometres from Deep Cove and Doubtful Sound to West Arm, Lake Manapouri.
In my opinion, there's nothing like standing there watching that big beast come through that mountain. Because in the back of your mind, it's always, will it really be in the right place? Is it really where it's supposed to be? And I felt really proud of the people. They worked hard to get it there, and they deserve to be really a pat on the back.
To get here, the TBM has used 4,079 cutter wheels. For the first time, it's possible to get through the new tunnel. Even after the hole through, there's about another 12 months' work needed to finish the project. First job is getting the TBM out of the tunnel, and the only way to do that is by breaking it up. One of the biggest, most powerful tunnel boring machines ever built is soon reduced to scrap. In pieces, the TBM is taken out via the maintenance shaft in the west arm headworks. What can be saved will be, but the cutter head is far too big to bring out intact, so has to be cut up. It's sent to Australia as scrap metal. 3 years ago, the TBM arrived in pieces shiny and new on a ship from England. Now, having drilled the new Tailrace tunnel, it's leaving in pieces, no longer shiny and well worn. The TBM's conveyor, which carried out the spoil, is dismantled and taken back out through the tunnel to Deep Cove. It's been sold and will soon be transported away. With the tunnel now bored, the next stage of the project is underway. These are precast invert segments, which have just arrived from Invercargill. They'll be positioned on the floor of the tunnel, part of the concrete lining to be used where the rock is least stable. Another recent arrival is the tunnel arch form, made to fit exactly inside the tunnel. This was purpose-built by the Italian firm Stifa and is being assembled outside before being moved into the tunnel for the placing of the concrete lining. In the tunnel, through the fault zones where the steel sets have been erected, the next job is encasing them in concrete. Once the tunnel floor or invert has been cleaned up, the precast invert segments are positioned. The concrete lining will protect the steel sets from the action of the water, which will eventually flow through the tunnel from the Manapouri power station. The more of the segments the crew lays, the smoother the operation gets. Working up the tunnel behind the invert crew comes the formwork. The 14.4 metre long structure weighs 600 tonnes and propels itself along the same rails the tunnel locomotives use. It's worked round the clock in 2 12-hour shifts. Concrete's made at the Deep Cove batching plant, and it goes into the tunnel by rail in bottle cars. Once the formwork is in position and concreting has started, there must be no hold-ups. That could risk what are called cold joints, a potential weak point in the concrete lining. As soon as the bottle cars arrive, the concrete's emptied onto the conveyor, which takes it up to a pump. Behind it, the formwork leaves the tunnel looking like the inside of a concrete pipe. The concrete's an average of 400 millimetres thick. It's pumped into the gap between the 9.25 metre formwork and the 10 metre tunnel. Every 24 hours, another 14.4 metres of concrete lining is placed. To complete the project, the tunnel lining has to be finished, railway lines and various utilities have to be removed, and the Tailrace channel has to be excavated. Then Tom Martin will have a message for Meridian's chief executive.
I'm waiting for the day when I can turn to Dr. Turner and say, Mr. Turner, your tunnel is ready.